We are Team CE9, and in this video we will be presenting an experiment that demonstrated mass transfer and diffusion in liquids and gases. So, first of all, what is diffusion? Diffusion is a form of mass transfer that occurs primarily in fluids due to a difference in concentration, where particles move from an area of higher concentration to lower concentration. The rate of this movement depends on the diffusion coefficient, which is a fundamental parameter in Fick's law of diffusion as shown, where J represents the mass flux, dc by dx the concentration gradient, and the diffusion coefficient, which will be calculated later on. Mass transfer by diffusion is crucial in industries like petrochemicals, food packaging, and water treatment. It ensures efficient separation and purification for processes like distillation, crystallization, and extraction, maintaining high-quality product. In food packaging, diffusion impacts material permeability, affecting food freshness. In water treatment, gas-liquid mass transfer optimizes energy and emission control. Innovations like Zule's eco-friendly advancements and new tray designs enhance efficiency. The objective of this experiment is to determine the diffusion coefficients for liquids and gases, using experimental setup, and to validate the diffusion principles by using the observed data. We are also aiming to investigate the factors influencing the diffusion rates, such as concentration gradient and temperature. Two sets of experiments were carried out to investigate the diffusion in liquid solutions and in gases. For the liquid solution experiment, we started by filling a measuring flask with 900 milliliters of distilled water. Then we filled the diffusion cell with 1 molar solution of sodium chloride until it overflows. After that, the diffusion cell was placed into the measuring flask, and the air bubbles in the capillaries were removed using a pipette. We then covered the capillary disc with water and inserted the conductivity probe. The magnetic agitator was then switched on and maintained at approximately 200 RPM. The conductivity value was recorded every 3 minutes, and the results were tabulated. The graph of conductivity versus time was plotted based on the data obtained. The graph shows a logarithmic trend as concentration gradient decreases over time. The difference quotient obtained from the linear area of the curve was 1.88 microsiemens per cm per minute. The coefficient of diffusion was then calculated using the equation with all the values converted to SI unit. The coefficient of diffusion obtained was 6.68 times 10 to the power of -9 meters squared per second. Some possible sources of error in this experiment are the impurities in the water or salt solution, leading to a systematic error in the data. Some potential random errors include the variation in the agitator speed or human error like inconsistency in timing.
The procedure followed in the gas diffusion experiment is demonstrated on this slide. The first step was to fill the diffusion capillary tube with acetone until it was 40 millimeters from the bottom. Next, we needed to insert the tube into the water bath so that it was exposed to the controlled temperature of 40 degrees Celsius. Finally, we needed to measure and record the time and change in acetone level in the diffusion capillary minute intervals to collect a total of 10 data points. In order to quantify our results, the Fuller, Shelter, and Giddings equation was used to estimate the diffusion coefficient of acetone in air. We then plotted the graph of the change in height of the acetone over the time divided by the change in acetone level. Using linear regression, we were able to find the value of K, the y-intercept of the graph, a constant that enabled us to calculate the diffusion coefficient. The estimated value for the diffusion coefficient was around 7% different from that calculated using our data. The systematic sources of error encountered were controlling the temperature of the water bath, as fluctuations could alter the diffusion rate, as well as the calibration of the movable microscope, which would both introduce consistent errors in measurement. The random errors encountered included human errors of recording the acetone level in inconsistent intervals, resulting in discrepancies in the data, and parallax errors in measuring liquid levels, creating difficulty in observing the acetone level precisely using the microscope. And in conclusion, in this experiment we measured diffusion coefficients in both liquid solutions and gases, illustrating the practical relevance of diffusion principles in various phases. The findings offered valuable insights into diffusion mechanisms and their industrial applications.
And finally, these are our references, and thank you for watching our video.